general relativity, step by step. Last time I proved this rather interesting and useful looking result here on the contraction of a Christoffel symbol of the second kind. So what I'm going to do now is show how to calculate the Christoffel symbols, and I'll show eventually, it might take 2 or 3 screencasts, but eventually I'm going to show what a massive saving of time this result is here, simply by showing how complicated the regular Christoffel symbols are. So I'm going to go back to my system here, my h theta system, h theta, there's a point x, y, x equals h, x equals h, and y equals h tan theta. So this beautiful, beautiful system here. And in this particular basis, the metric tensor looks like this. See if I can get this right. It has got a sec squared theta there, and I've been using this all along, so I'm not going to demonstrate it here. H sec cubed theta sine theta, h sec cubed theta sine theta, it's symmetric of course, h squared sec to the 4 theta. Now that's the h column, and that's the theta column, that's the h row, and that's the theta row. So for example, g theta theta is this term here, h squared sec to the 4. Now I need to invert it. That's the matrix inverse. That's g. That's the matrix inverse of this matrix here. And I can never remember the formula. As much as anything, I just wanted to show you how complicated all this stuff is. Let's work out the determinant of g, det g in this particular coordinate system. That's h squared sec to the 6 theta. It's the product of these guys. Minus h squared sec to the 6th theta sine squared theta. H squared sec to the 6th theta, 1 minus sine squared. H squared sec squared theta cos squared theta, that's the 6th, I'm sorry, equals h squared sec to the 4 theta. So there's the determinant of the metric tensor. So the matrix inverse, Gij, well, let me just remind myself what the matrix inverse for a 2 by 2 in general is. A, B, C, D minus 1 equals 1 over the determinant, switch and swap. So you switch and swap the signs, or is it swap and switch? A, B, C, D, that should be a D, and that's minus C there. There we go. So I'll just use that formula. So the inverse metric is 1 over h squared sec to the 4 theta, which is the determinant. Switch and swap. H squared sec to the 4 theta, because it's that term there, sec squared theta, and then that's a minus h sec cubed theta sine theta, and it's symmetric, sec cubed theta sine theta, which goes there. So let's just work out what that is. That's a 1, got various terms, that's a minus h sine theta cos theta, sorry, that's h to minus 1. Is that positive or negative term? These are positive, so these are going to be negatives, that's right. So this term's minus h minus 1 sine theta cos theta. Yeah, that's right. And what have I got here? H to the minus 2 cos squared. So there's my inverse, and that is my metric tensor with contravariant components there. Okay, so what I'm going to do, I'm going to evaluate this term here, not even contracted, I'm just going to evaluate one term of it, just to show you how it works. I'm going to evaluate Christoffel H. Notice that I'm using the letter H as a description of the index itself. I'm not using an I, a J, a K. I'm not using general tensor notation, because I might want to work out that, or this, or so forth. So I'm using these letters here as a description of the actual index itself. I can't sum over h because h is just h. So for example, last time I had j, for example, and that's summed over I. But this notation doesn't work here because that h is a particular coordinate dimension. So the general term I, j, k. Now these are indices, so that's a half g. Now let's see if I can get this right. Oops. Let's see if I can get this right. That I there is this I here, and it's going to sum I, j, k, l over di g something something by di x something plus di g something something by di x something else minus di g blah blah by di g blah. Pinching a little bit here. Okay, so the summation index L here, it goes once in the first slot, once in the second slot, and once downstairs there. What have I got left? I've got a J and a K. It's got to be a J and a K and a J, and a J and a K. Always using the fact here that the metric tensor is symmetric. Okay, well that's great. So what I want to do now is to evaluate this. So that tells me that I equals J equals K equals H. It's rather a peculiar notation because this letter here is different. It might have been a theta, but it is in fact an H, and these are just regular indices here. So that equals a half, and I'm going to leave it in this rather sort of hybrid notation. So it's going to be G H L, where L is the summation variable, times di g by di something plus di g by di something else minus di g by something else. And I'm going to fill the bits in. So it goes an L there and a dot, L in the second place, and I'm just going to leave it as di x L there. Now what have I got left? I've got everything else is an H. H, 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 H. But it's still summed over L. And L is going to be equal in turn to H and then theta. Oops, what's happened there? Oh, here we go. I don't like it when it does that. I think it's because I hold the pen wrongly. Okay. Oh, it's happened again. It's not ideal, this. Okay. Equals. Well, first of all, I'm going to set L equals H, and then secondly, I'll set L equals theta, and then I'll sum those. So we've got a half G, and I'll just write it out, and then I'll expand using the proper definition. L equals H. So we've got H, everything's an H now, because all the variables, all the indices were H, because it's H and H and H, and the summation variable L is also an H. So I'm going to write it out, even though there's cancellation that's going to happen in a minute. Di H, di G H H by di H, minus di G H H by di H. We'll see that this is a lot simpler than it looks. That plus a half G, now things get a bit interesting, H theta. Where we had an L, I'm going to substitute a theta into it. Okay, let's just pinch in a little bit. Di G theta H by di H. That's that term there. Plus, but with the L replaced by theta. This one is going to be di G H and then theta by di H. You see, and because it's symmetric, those are the same. Minus di G H H by di theta, because XL is equal to theta. Well, now, that's great. Now, can we use any simplification? Well, yes, we can, as a matter of fact, because GHH, this is G subscript HH, which is the irregular metric tensor, which is sec squared theta here. And so what that tells me is that di GIJ, di GHH by di H equals di by di H of sec squared theta, which equals 0, because this term here does not have an H in it, which is nice. So that makes my life a lot easier. That means that this whole bracket disappears. There's extra cancelling as well, because these two terms cancel out anyway. But the whole thing, and I can use a red, that cancels out to 0, which is quite nice. Back to black. So what have I got left now? I've got Christoffel H equals a half G H theta. I think it's a good idea to do cancellation into, or, well, separate out the cancellation as much as you can. So, first of all, I'm going to observe that these guys are the same. D theta H by di H minus di G H by di theta. Great. Equals 1/2 times H G with contravariant indices H and theta, so I'm going to have to scroll back up. It's this guy here, minus H minus 1 sine theta cos theta. Minus H minus 1 sine theta cos theta, that's that term there, times, open brackets, 2 di by di H of di theta H. Let me remind myself what that one was. I'll write it in. It's di by di H, and then from up here, wherever it was, oh, there it is. No, that's the contravariant one. It's H sec cubed sine. H sec cubed theta sine theta. No, the bracket shouldn't be there. Minus di by di theta of G subscript HH, and that was just sec squared. Okay, after a while you get a flavour for this. Have I got a 2 missing? No. Equals minus 1/2 H minus 1 sine theta cos theta times 2 sec cubed theta sine theta, because I'm differentiating that term there with respect to H, minus di by di theta. So that's 2 sec theta times the differential of sec. And what's the differential of sec? That's sec squared sine, isn't it? Sec squared theta sine theta. Aha. And these guys cancel, look. Bonk, blomp, blomp. They cancel because they're equal sign. So it doesn't matter what this term is here because everything cancels out. Just pinch in a bit. Equals 0. So let's go through the whole process. Let's go through the whole process again. We're looking at Christoffel symbol H, 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 with H on the top and H, H on the bottom. We've taken the definition, we've summed over L, which took in turn the values H and theta. Whole bunch of cancellation happens for different reasons, and we're left with this rather, I won't say mysterious, but the fact is that this term here is equal to that term there, and so that the difference is equal to 0. And this is typical. Quite often when you're calculating complicated tensors, the Riemann tensor in the Riemann curvature tensor in particular, what happens is nearly all the terms cancel out. I mean, in theory, there might be 64 or 256 components, but in practice, very nearly all except for 3 or 4 of them will cancel out. Certainly if you've got formulas like this. If you're doing numerical work, then you've got to account for them all. But there we go. Right, so I'm going to stop there. What a pain. Oh yeah, the thing I want to observe here is not so much, oh well, the tensor is equal to 0. Sorry, it's not a tensor, is it? The Christoffel symbol equals 0. What I want you to pick up is how difficult it is to manipulate these quantities and how much you need to be in control of superscripts and subscripts and the summation convention. Not to mention the difficulties of differentiating sine thetas and sec thetas and stuff like that. Right, I'm going to stop there.